Officer of SAE-UTM, who also hold the position as the Director of Automotive Development Center in University Technology Malaysia. And of course, our special guest for today, Dr. Farhan bin Azmin from Ricardo PLC, United Kingdom, for making this webinar possible. Before I introduce myself, may I have a favor to check if my line or my voice is clear for everyone in the chat box, as well as Dr. Azman and Dr. Farhan?
Yes, sound check.
Okay, thank you. It's clear. Okay. Thank you so much for responding. My name is Hilfai Sufri bin Shamsuddin, a registered member of SAE itself, including SAE Malaysia, and currently a postgraduate student in miniature cooling system with AI research in University Technology Malaysia. Tonight, I will be your host, and it is my pleasure to welcome everyone in this webinar of SAE Malaysia 7th lecture series, Calibrating Powertrain using MATLAB by Dr. Farhan bin Azmin. But before the main event, I would like to call Dr. Azman, the advisor of SAE-UTM and the director of Automotive Development Center, UTM, to say a few words.
Okay. Thank you, Hill. Can you hear me?
Yes, it's clear. Is it clear?
Alright, okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good evening. To our guest speaker for today, Dr. Farhan Azmin from Ricardo PLC, United Kingdom, to the SAE Malaysia committees, to all honorable professors, lecturers from universities across Malaysia, to professionals from the industry, to fellow students from all universities around the world, to family members and friends. Alhamdulillah, we are thankful to Allah Subhanahu Wa Taala for being able to gather tonight to attend the SAE Malaysia 7th lecture series by Dr. Farhan Azmin from Ricardo PLC, live from United Kingdom. As the advisor of the UTM SAE student chapter, and on behalf of the committee, I would like to thank everyone for attending tonight's session. Congratulations and well done to the UTM committee for being able to plan, organize, and then implement this lecture. First of all, I would like to inform that this lecture is not only about the content, but also a glimpse about the current global automotive industry and inspiration for all students to go global. Sky is the limit, inshallah. Ladies and gentlemen, Ricardo PLC is a well-known engineering and consultant company in the global automotive industry that specializes in the transport, energy, and also resources sectors. Their work extends across a range of market sectors, including passenger cars, commercial vehicles, rail, defense, motorsports, energy, and also environment. Their client list includes transport operators, manufacturers, energy companies, financial institutions, and government agencies. Today, we are very honored for the opportunity to have Dr. Farhan Azmin as our guest speaker. He is the Senior Project Engineer and Machine Learning Specialist for Software Control and Calibration in Ricardo PLC, United Kingdom. Briefly about Dr. Farhan. I've known Dr. Farhan for 13 years now. We first met when he came to Proton in 2008 to do his internship for his engineering degree from IIUM under my supervision. Because of his excellent performance and interests, he was then later absorbed as my staff to be the Powertrain Development Engineer in 2011. So during this service with Proton, he has contributed to many engines and ECU testing development projects, not only in Malaysia, but also in other countries such as UK, Europe, and also China. Then, in 2012, he moved to Loughborough University, United Kingdom, to pursue his PhD in the area of engine calibration and advanced control. Upon graduation, he had the opportunity to join Ricardo PLC in 2015. And today, Dr. Farin is now the Senior Project Engineer and Machine Learning Specialist. Congratulations, Dr. Farin. It has been a tough journey, but you kept on to pursue your dreams and also passion. So without further ado, I would like to pass back to the moderator for all of us to join welcoming Dr. Farin for the lecture today. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you to Dr. Azman for the short briefing. As we all know, the webinar is organized together with SAE-UTM and will be presented by Dr. Farin bin Azmin. This program aims to promote AI implementation in various technology in Malaysia, where today, Dr. Farin will demonstrate specifically on how he applies his AI configuration of particle swarm and genetic algorithm using MATLAB for optimizing powertrain calibration. Questions can be asked through the chat box, but to be answered during Q&A session. Without further ado, let's invite our speaker tonight, Dr. Farin bin Azmin. Go ahead, Doctor.
Hello, can you hear me clearly?
Yes, it's very clear, Doctor.
All right, okay, I'm going to start now. Thank you for the kind words, Dr. Azman. So, okay, let's start with the presentation. Hold on. Let me share my screen. Okay. Can you see my screen?
Yes, it is quite clear. For everyone, can just write inside the chat box if it is clear.
Okay. Okay,
Seems like it's okay.
Yep. Okay. So the topic today is about MATLAB calibration and simulation of Powertrain. So basically, I'll present how we apply ML and AI into parameterization and optimization. Okay, so Dr. Azman has presented my profile, so I don't need to go through it again. So, but basically, my main responsibility at Ricardo is developing cutting-edge machine learning tools for automotive and powertrain applications. And also, I develop bespoke algorithms for powertrain purposes. So I've provided here my LinkedIn if you want to see my profile. So Ricardo is quite an old company. That's been about more than 100 years now. So it was founded by Sir Harry Ricardo. So we are a global strategic engineering company. We have offices around the world, and we have about almost 3,000 engineers across the world. So we solve complex problems ranging from automotive, energy, and rail, and also defense. So for the presentation today, I'm going to cover a few topics. So these are the topics. So it's model, strategy, simulation, and then parameterization, and how we use machine learning and artificial intelligence to accelerate parameterization. There are some new types. So we have been pioneering machine learning quite early, more than 20 years. So it was cutting edge during that time. But now the innovation in ML innovation in automotive is quite slow, especially for powertrain. So there's a lack of high impact innovations in this area. So in the future, what we want is to get more smart ML and AI engineers to invent new tools and processes to help us to complete projects quickly. So my role at Ricardo, so I'm currently working as machine learning engineer. So I get this question a lot. What's the difference between data scientist and machine learning engineer? So there are many descriptions, and also there's not clear difference between these two positions. So this is what I have observed in my company, and so I've made this flowchart to distinguish the differences. So both of them we always get data to work on. But for me, I use a lot of mathematical formula and then convert them into algorithms where I can develop tools and create new processes which can be used by domain experts to deliver products. So we also have data scientists working in different areas. They can use a lot of data to get data insights, which can be used by both management and domain experts. So the management can use the results for business decisions. But we always work together. The data scientists can advise us on what model to use and which algorithm to use. So this is, I believe, what is happening at my company now. So this is where I'm working as now. So this is the agenda for today. I'll be covering a basic introduction of ML, model, and optimization. And then we go through to model parameterization and what is it about. And also how we use ML and AI in parameterization. So this is quite a new topic where we're developing new techniques for making parameterization faster. And then I'm going to talk about advanced optimization, where we use evolutionary algorithms for some case studies. Lastly, I'll be comparing which language to use, MATLAB or Python. So what is machine learning and AI? So to understand what is machine learning, so you need to look at AI. So in AI, there's a lot of subtopics or areas, such as image processing, machine learning, optimization, planning, and control. But today we'll be covering machine learning and optimization. They are both quite important areas in artificial intelligence, because without these two, you cannot run any optimization or model to make the AI smarter. So it's quite important areas to be covered. So first, before that, I'll be switching between presentation and MATLAB. So because I'll be doing a live demonstration for some of the cases. So the first thing I want to cover is what is model. So model is basically a representation of a system in mathematical form. So we use this a lot for predicting engine responses, emissions, driver behavior, and many more. So why we need this model? We want to repeatable outcome. We want to predict future outcomes, and also we want something fast that we can run in optimization. So these are the three basic types of models that is possible. So first is the physics-based model. So I have here a simple mathematical model where you have parameters and it can make some predictions. And then this is using machine learning. So you have a lot of data. You can train a model so that it will behave as you want it to be based on the inputs provided. And then this is a hybrid model where you can combine a physics-based model with a machine learning model. So they can work in series. So I'm going to do a live demo how we can do these two models with MATLAB. So I'm going to switch to MATLAB now. Okay, so I'm going to use this example. So it's just a simple formula. It's this one. Oh no, this one. I hope I don't crash my MATLAB today. So okay, I have here a simple physics-based model with inputs. So here in the model, there's a simple mathematical formula which is consists of these parameters and also two inputs. So if I run this, to run this. So it's just a simple output. So what we want to do is to create a machine learning model that can replicate these responses. So what I want to do is how we can create a machine learning model out of this physical model. So I'm going to apply some random inputs So usually we use APRBS or dynamic DOE for the responses for training a machine learning model. And you can see here, so these are the inputs to the model. So we just provided random points to the model, and then measure the output, and also record the inputs as a file. So this is the file. So I'm going to export the model. So sorry, export the inputs to the machine learning process. So these are the two inputs and this is the output. So I'll use this data to create a machine learning model. So in MATLAB, it's quite simple. So I'm going to start the session. Okay, select the responses. So this is the response that I want to model, and just okay. So these are the written model. To use this one and train. Okay, now it's done. So you can see the prediction is quite good as well. And then use it in the machine learning. Save this. To save this. So now I have the file. So it's called train model. So I'm just going to run another set of subsystem. So it's this one. So in here I have a block which calls this model. So now we want to test if the model can make accurate predictions of the physics-based model. Let me link this. Run again. Okay, let's check. So now you can see the yellow line is the physics-based model, and the blue dash line is the data-driven model. So it's quite accurate. So if you in the regression learner app, you can create your own function where you can create your own modeling process. So it's quite easy. So MATLAB can automatically generate the script where you can reuse it for any. Okay, now let's make the problem a bit harder. So I'm going to okay. So now I'm going to create a hybrid model that combines both physics-based model. So how we can do this? So it's quite easy. So basically you just again provide random inputs to the physics-based model. So this is the part 1 of the physics-based model. This is the part 2. So the part 1 contains only half of the physics-based model, and then I have the full model. So consists of part 1 and part 2. And then you feed in all the inputs to the both models, and then you record the outputs. And we will use this one to train a machine learning model for predicting part 2. So open again regression learner. Start a new session. So check. So extract the outputs. So this is the output that I want to use. So I have more inputs now to the model, and this is what I want to predict. So now I'm going to start a new session. Okay. So now I specified column 4 as the response that we want to predict, and these are the inputs. So start session. And then select your model. Train. Okay, the process is complete. So the prediction is quite good, and now we can export the model. So let me just train model 1 and save it. So now I have the hybrid model here. Okay, next I'm going to use that model to predict some outputs. So I've used the same inputs as the above subsystems and then provide them into the part 1 of the model. And then the output from the part 1 will be used as the input for the part 2 of the machine learning model. So let me link this. So now I'm going to run it. So we can compare the performance between the physics-based model, data-driven model, and the hybrid model. So you can see they are quite close. So you can see actually the hybrid model is much better than the data-driven model because it consists of some part of the physics-based model. Yeah, so it's quite easy to use. So Matlab has this regression learner app where you can use the GUI to make models. So it's quite easy to use. Okay, next. So I'm sure you're wondering how does the model looks like, the machine learning model. So this is one example of a machine learning model that I've created using my PhD. So I've been developing my own algorithm and creating my own model. So this is one example of BFFC model. So it contains a bunch of lines which can represent a system. So you need some sort of optimization to fill in the model parameters. So how we use this model, you can, if I put some inputs here, change this. Oh, I'm going to skip this. If I run the model here with some inputs and do some sweeping, so you can see. So I've put some inputs of VGT into the model, and you can see this is the BSFC profile for this VGT sweep. So it's using this BSFC model. Okay, so that's for the modeling part. Okay, so some applications of machine learning model and hybrid models. So how we use it for in Powertrain applications. So we can combine static and model. So at Ricardo, we have WaveRT, which is a simulation software. So we use this to predict EGR and boost. And then we also use a machine learning model to predict the heat release. And when we have another machine learning model which can predict emissions and fuel consumption. So when you link all them, we can get accurate emissions prediction. We also have another set of flow which we use a machine learning model and a dynamic model. So this dynamic model is actually a machine learning model wrapped with a dynamic structure. So it allows time series predictions. So we use this to predict time series EGR rate and boost pressure. So they will provide more accurate or realistic tracking of the EGR and boost. And then we use this as input into a machine learning model to predict emissions. So as you can see here, you can this method is quite close to the actual soot emissions for diesel. And this method is the blue line. So it's much less accurate than this one. So we have been using this model for calibration optimization to produce ECU maps, which we can use in actual vehicle. In aerospace, we can also use a machine learning model for surrogate modeling. So instead of having to run CAE or complex CFD simulations, we can replace it with surrogate model, which we have trained to do some optimization. So another good example of machine learning model is in model-based calibration. So so we have been using this a lot, where we have created engine model from engine testing to create optimization maps for engine applications. So what is a model? What is a powertrain model or strategy? So in an ECU or electronic control unit, it can contain a lot of subsystems. So these subsystems are used to replicate some behaviors of the engine without having the actual sensor, which can be expensive. So they are basically physics-based model where you have a lot of calculation switches or lookup tables. So we use this to make predictions of some engine responses. So it can contain hundreds of parameters, and the subsystem can be quite complex. It can be 10 or 100 times this size of model. So it can be really complex to optimize. And then, so what is optimization? So optimization is quite important for AI and machine learning. So we use them to get best selection of parameters. So I have here example of a simple problem where I need to find best parameter 1 and best parameter 2 in this problem space. So it's basically just a big loop, for loop or while loop, where it iterates to get to a good cost or model output. So it's just a simple, this is just a simple process. So I'm going to show you the code on how we can do this. So it's quite simple to construct your own optimizers. So this is just a simple gradient descent optimizer. So first you just need to specify your points, and you need to specify your optimization settings, and then you need to have a problem. So in this case, my problem is this. It's just a simple surface problem. So if I run this, so imagine this is my problem, and I want to find the best solution from this problem space. So I just want to find this point from a random starting point. So let me run this section. So what I did was I've just created a big for loop which iterates through a gradient descent optimizer. So I have here a simple function objective, which is my problem. And then I've also get the gradient of this problem. So in terms of X and Y directions. So we use gradients to help the optimizer to know which direction to go. So without gradients, the optimizer will just go random directions. So that's not good. So what contains in the big loop is the gradient, the process to get the gradient, and then we add up the gradients into the parameters each time, and for each iteration, and then we have our function tolerances, and then once you have the optimized point, we just update the current point, and then we evaluate the problem. So it's quite a simple optimizer. So let me run this. So I've started from this point, so it's just finding the best point in this problem space. So it's quite an easy problem to solve. So if I take this, so I've started from here, and then it goes down to here. So it needs the gradient information to know which direction to go. So otherwise the optimizer will not know how the system will behave. So it's just a simple process. And then in MATLAB we have functions to do this automatically without having to create your own for loop. So we can use fmincon. It's quite a popular optimizer. So I'm going to apply the same problem to fmincon. So it's this one. So I'm going to use the same problem, problem objective, which is this one. And then I'm going to provide a start point. So let me run this. So this is the optimized point, so it's quite fast. And then of course you can apply your own boundaries. So let's say if you want to control the parameters, so I've made the boundary a bit smaller. So if I run this, so you can see it's 0.4 and 0.5. So it's now a bit smaller. So of course you cannot see anything now. So we can put functions to display or to plot the optimizer. So I've put the same display into the optimizer. So you can see fmincon has smarter algorithm than the big while loop. So you can see it can find solution in less steps compared to my own while loop. So this is the optimized point. And then of course you can apply your own gradients to the optimizer. So there's an option where you can switch on the settings, and then you can fit in your own gradients to the optimizer within the function objective. So it will work similar as the previous method. Okay, so I'm going to skip this now. Okay, and then we go to what is model parameterization. So in an ECU, it can contain many subsystems, and the subsystem can depend on each other. So the most common one is exhaust temperature model, where we use this to predict temperature predictions of exhaust. So these are the typical inputs to the model: engine speed, engine load, and engine ignition angle. So we use the temperature predictions for the fuel control, where we can accurately determine the fuel quantity required for that specific operating point. So this is how subsystems in ECU work together. So this is what we want to parameterize today. So and in an ECU, it can contain many maps or parameters throughout the strategy or model. And without optimized parameter, you cannot get correct predictions of the engine responses, so which is not good. So what we need to do is we need to optimize the parameters. So this is a typical process of parameterization. So basically, it first starts with data collection, where you can do this on test bed or on vehicle. So what we want to do is to use a physical sensor and then compare it with the ECU subsystem and then check the error. While doing that, you can record the measurements. And then you need to recreate the strategy in Simulink, where you can run simulations of it. And then you need to run the Simulink model to make sure you have construct the Simulink correctly. So you need to compare with the results that you get from the data collection. Once you have the model and it has been validated, you can use in an optimization process or with optimization tool. And then once you have the optimized maps, you can use it in actual engine or vehicle with the maps loaded into the ECU. By right, you should get the error quite close to the actual sensor. So this is a typical parameterization process. So one of our tool for optimizing strategies is called model parameterization tool. So it's the standard tool that we use for all powertrain development projects. So it is an interactive tool where it can help engineer to quickly set up problems in the tool and then automatically run optimization. So it can help engineers to fill in maps quickly without having to manually type the map values. And also we have program an interface where they can they can automate the optimization process in sequence. So it's quite easy for the engineers to use. So the tool can automatically detect blocks in Simulink, so you don't have to do it manually. And the tool comes with automatic map parameterization. It has advanced optimization routine together with map smoothness constraint and also the monotonicity constraint. So it's quite an advanced routine with we have many options for optimization based on the problem. So I'm going to do a live demo of this tool so that you can understand it further. So let me clear this. So this is an example of exhaust temperature model strategy. It's quite a simple one. It has several subsystems and also some maps. So this is the map that I want to optimize. So I've constructed this Simulink based on the client's reference that they have given to us. Close this. And then we have the initial maps that we can use as starting point. So this is a typical maps format used within the automotive industry. So this is called a DCM file. It contains all the maps that initial maps for a particular ECU. So we will use this as the starting point. And then we have test data, which we have recorded from vehicle or test cell. So let me inspect this data. So I'm going to load this that file. So these are the inputs that will go into the strategy, and this is the measurements from the exhaust temperature sensor that we want to parameterize, so that our strategy can accurately predict this exhaust temperature profile. Okay, so I'm going to load MPT. So this is MPT. So now I'm going to create a project. I'm going to load a test file. So this is the file. Contains all the channels that are required to run the strategy. And then load our initial start points. So this is the map that I want to optimize. So I'm going to click OK. And then I can view the map using map tool. So it's one of the feature in MPT. So I can load this map. So this is the map that I want to optimize. So this tool is quite interactive. So you can sometimes when the map is quite big, so engineers needs to analyze the map and check for spikes or any strange values within the map, so they can use this view cross-section feature to analyze the map. And then we can also check the bounds for optimizer to make sure it's within the sensible range. Okay, now I'm going to optimize it. So next, I need to load the Simulink.
Ikan telur. Sorry, there will be a technical issue for a while. I think the internet a little bit of problem. Right now we are waiting. We are reaching Dr. Farron.
Can you hear me?
Oh yes, it's already okay.
Okay, sorry. Lost my internet connection. Okay.
Okay. Thank you, Doctor.
Okay. Can you see my screen?
Yes, yes. Everything's clear. It's back to
Okay.
normal.
Okay. Sorry about that. Okay. So I think I'm going to skip the MPT stuff because my internet is not working as expected. So this is a video of how MPT optimizing a simple exhaust temperature model. So if you hit run, and you can automatically make corrections to the initial map so that you can get correct predictions of the strategy, so that you can emulate the actual sensor. So now it has completed the optimization process. So it's quite easy to use. So next, how we use ML and AI in parameterization. So what we want to do is to emulate sensors on engine, because sensors are expensive. So we don't want to have expensive sensors on engine. So when we want to emulate this through a model, so we will be embedding subsystems in the ECU to emulate this. And then if we provide inputs and optimize parameter to the subsystem, it can make predictions of the sensor. But if you provide an unoptimized map, the error will be higher. So what we need to do is to recreate the subsystem in a Simulink model, and then use the model in an optimization process, and use the optimized parameter in the ECU. So usually the subsystem is not provided by our client or supplier. So this is a typical problem in for consultancy like Ricardo or many OEMs. So what we need to do to get the model. So we need the strategy documentation from our client or the hardware supplier in PDF, and then we need to reconstruct the Simulink model manually, and then use the model in the optimization process. So reconstructing the Simulink model is quite labor-intensive process. It's not easy, and usually it can take 2 to 3 weeks to just develop the Simulink model, and maybe another 1 or 2 weeks for validating it. So it's quite a labor-intensive process. And then the optimization itself is computationally expensive, because you need to evaluate the model thousands or millions of times every iteration. So it can take very long time to get a good and sensible maps. So how we solve this problem? So we use ML and AI technique to automatically generate PDF into Simulink model. So we don't have to do it manually. The tool that I've created called Ricardo Trace. It's using deep learning and ML and AI to automatically generate Simulink models. And then we also use this method using surrogate model to simplify a strategy so that we can reduce the runtime and make the optimization finish quickly. So we have developed a tool called Ricardo Trace. It's for converting PDF document into Simulink. So we combine deep learning model, image processing techniques, and also AI for the line tracking, and OCR, optical character recognition, so that we can identify the blocks and reconstructing the Simulink model. So using this tool, we were able to convert a simple strategy in 100 seconds Meanwhile, a human developer needs 685 seconds to do the same task. So we are making this comparison not for checking who's the fastest, but we want to predict the number of the time it will take if we have more components per diagram. You can see here the development time rises exponentially with higher number of components per diagram. So I'm going to do a live demo of this tool. Hopefully my MATLAB will not crash. So I'm going to load Ricardo trace. Okay, this is the Ricardo trace tool. So I have here a simple strategy. This one. So this is a typical format of a strategy. It's quite similar to the one from hardware developer. So you have diagrams of the strategies. So I have here just a 6 pages strategy. Usually an actual strategy, it can contain between 50,000 pages to 100,000 pages. I'm not making this up. This is actual that's the actual number of pages for actual hardware. So this is just a 6 pages strategy. So I'm going to convert some of the pages, some of the images into actual Simulink model. So this is Ricardo trace. So I'm going to load the strategy. Okay, I have here this subsystem that I want to convert. Just select OK. Select the region of interest. And then you can select the title. And then I can do the same for another diagram. So select this and select the title. I'm not going to do all strategy because I don't have all model because I don't have much time. So I'm going to do just 2 diagrams. So now it's importing high quality images so that we will not lose any pixels during the detection process. Okay, next I'm going to so these are the images that has been extracted from the PDF. So now I'm going to use a shape detection algorithm to detect the blocks. So this is the region of interest that has been detected for all blocks, and also it has captured all the names of the blocks and also arrows. And then I'm going to detect the lines. So this line detection is using AI method for detecting the lines. It is an agent-based line detecting system with sensors positioned in front of the agent. So this is to check for any gaps in between the line using the pixel information. So we have been testing a lot of algorithms. So far this is the most robust algorithm that we can find, because we don't want the user to to change parameters for the line tracking system. So we just something that is robust and that can work straight away. So now it's detecting all the lines. The detection is actually fast. I've purposely make it slow for animation purposes. So of course we can speed this up. As you can see here, this is quite challenging, this area, because there's a gap between the lines. So the agent can create a temporary bridge that can pass this gap and continue finding the lines. Okay, now it has detected all the lines, and of course you can make changes to the line if you are not satisfied with the detection. So now I'm going to run prediction. So it's going to identify what is this block in Simulink. So now it has identified this one as imports. In this process, it's using a lot of detection process. One of it is using deep learning to identify, to classify the block image. So now it has detected this as a subsystem. Okay, now I can automatically create the Simulink model. So now it is using a Simulink controller to automatically generate the Simulink, so I don't have to do it again. So it's using all the information from the detection process to generate this. Imagine if you have 100 of blocks and you have to type the names manually, or maybe you have hundreds of inputs and outputs. It can make your life difficult. So this tool is supposed to help you to skip some of the processes. So this is the automatically generated Simulink from the detection process. Okay, close this. So back to the presentation. So another method how we can improve the parameterization is using surrogate modeling. So imagine if you have a very complex subsystem or strategy, you can replace some of the complex part of the strategy with a simpler machine learning model, just leaving the subsystem with parameters to optimize. So you can combine this simplified strategy with a machine learning model to reduce the runtime. So here I have a simple air path strategy for predicting MAF or mass airflow of an engine. So for that subsystem, I managed to reduce the runtime from 1.03 seconds to 0.7 seconds. So that's reduction of 0.3 seconds. So this number looks a bit small, but actually when you are running optimization, you might run this 1 million times or 100,000 times. So if you multiply this with this improvement, you can get significant reduction in the optimization time. So it's quite important for us. So while even though the model has been reduced, but you can see the model error is quite low compared to the full model. So this is what we want to apply in the optimization process. So it can support both static model and dynamic model. So at the moment, the tool that I've made can only model using static model, but in the future we will be using deep neural network for characterizing the computationally expensive region to for time series problem. And then the next topic I'll be covering is about advanced optimization. So why do we need advanced optimization? So so this is similar as the previous example. It's quite a simple problem where you have one solution in the problem space. So this is quite easy to solve. It's not challenging. So in a real engineering problem, we have several solutions distributed across the problem space. So the values in the problem they are called local minima. But within the problem space, you might have a global minima. So this is what you want to find, the lowest value in the lowest point in the problem space. So the problem with the gradient based optimizer that we have used previously, the remember the big while or for loop. So that is a gradient-based optimizer. So the problem with that optimizer is sensitive to the start points. So imagine if this is your start point. So the optimizer will know can correctly direct the result to this valley, so to this local minima. So this is okay, but if this is the start point, so you don't want to get stuck in this local minima. So what you want here to get to this point. So if you start from this point, you can get to the global minima. So this is what you want actually. So it's quite difficult to get a good start point. So we need an advanced optimizer to handle this problem for us. So one of the method is using a stochastic approach. So so in this problem, I'm using a genetic algorithm to find the global minimum. So it is a process that mimics biological principle to find the best set of parameters through these GA operators called selection, crossover, and mutation. So here I have a simple example of how GA finds the global minimum. So the GA is making it's mix and matching the parameters to get a good population which can find the global minimum. So it's just looping this process and find this. So however, this optimizer does have a setback. It's quite a slow optimization process, but there's a way to make it this faster, but I'm not going to cover it today. So one of the application of GA is in diesel engine controller problem. So imagine if you have a multi-variable control, you can have thousands of parameters to optimize. So this is a simple control problem where you have a plant model, and plant model feeding states to the model controller, and the controller outputs the VGT, EGR, and throttle positions. So we want a good tracking of these responses. So this is a typical diesel engine controller problem. So what we want the controller is good controller stability and good tracking and low steady state error. So this is what we want. So it's quite challenging to get good controller performance because you have a lot of parameters to optimize. You have no start points, and the model runtime is long model runtime and also tight constraints. So how to solve this problem? We can use LQR. So in optimal control theory, LQR itself is an optimizer. It can determine the feedback gains for the controller. This one. Sorry. So you can use LQR to get the feedback gains for the controller, and then but in order to do that, it needs design weights. So the design weights are Q and R matrices. So usually people will manually change the matrices and then feeding it into the LQR, and that get the controller performance, and then repeating the same process again until you get satisfactory controller performance. So this is quite a labor intensive process. Imagine if you have 9 times 9 map matrix, so it's going to be difficult for you to make changes to the values. And also if the values they don't have the same scale, you can have a very small number or very big number, such some value you might have maybe 0.9, or some maybe you have 9,000 or 5,000. So it's quite difficult for you to play around with the number if you're doing it manually. So we need something to help the LQR to get a good design weights. So what we did was we combined genetic algorithm with this LQR. So we put GA on top of LQR to get a good Q&R design weights, and then we loop the process many times, and then evaluating the plant model to meet the target response. As you can see here, I have a simple animation of the process. So the problem is to optimize the K gain maps so that the blue line reaches the black line, which is the target. So this is what we want. But in order to do that, get a good Q and R matrices. So we use genetic algorithm to determine this for us, and then we'll just loop the process many times until we get good tracking. So this is one example on how we apply GA for a controller problem. So you can see here, it's making changes to the Q and R matrices automatically. So we don't have to type it manually and keep evaluating problem. It's going to take a very long time to do that. Okay. Next, how we use GA is this is a simple example that I've developed to solve F1 power unit selection. So this is an old example that I've created. So for the 2018 season, they are only F1 teams are only allowed to use 3 power units, and each of the power unit, they have different characteristics. They have different remaining useful life, different performance. So teams needed to make selection on which power unit to use for each of the races. So so this is an optimization problem. So they need to make the selection so that they can how do you say, maximize the power usage, and also to make sure all the power units survive until end of the season. So I've created a power damage unit, power unit damage model based on piston wear rate and also power reduction. So this is a simple model that I've generated. It's using race distance and track ambient temperature, which can predict the power unit remaining useful life and also the power unit performance. So I've applied GA in this problem. So it starts with these initial conditions. So I have these 3 power units with different remaining useful life and also different performance. So this will be my starting point, and the GA will keep on creating a random power unit selection, and then try to get the best best selection that can meet the constraint or the objective. So I've also provided the track info with average ambient temperature into the power damage model, and this will give me the power unit performance reduction and also the remaining useful life. If we're not using any optimizer, if you randomly selecting power units, so some of the power unit will not survive until end of the season. So like this one, you have some power units failing mid-season. So we don't want this. So we use GA to make the selection automatically. So this is the result. So you can see here, so the blue line is the optimized selection. So 3 of the power units survive until end of the season, and also the power reduction is kept minimum until end of the season, meaning that we managed to maximize the performance. So these are the power unit selection for each of the race. So I can do a live demo of this, but it's not that interesting. So switch to desktop. So I've here the track information, and also I've initialized the RUL and also the performance of the power unit. And then I've set up a GA optimizer. So this is a MATLAB function. So it's using mixed integer optimization process. So I'm going to just run this. So there's nothing interesting to see. There's no animation. It's just producing results. So now it's optimizing the problem. It's different selections of power unit and try to meet the function objective and also to meet the constraints. So as you can see here, so I've managed to make all the all of the power units survive until end of the season, and also I've kept the power reduction to a minimum. So the gray line is the some random results that coming from the optimizer. So this is one example of how we can use GA selections of Powertrain. Okay, back to the presentation. Next method of evolutionary algorithm is particle swarm optimization. So it's quite a complex optimizer, but I've put some reference for you can read. So it's basically putting particles in the problem space, and each of the particle can communicate with each other. So they can influence other particles so that they can move in the same direction. So let's say if you have several particles in the problem space, so they can communicate with each other to find a global minimum. So now you can see all the particles are heading to the same direction. So some of the applications of PSO, you can use it in intelligent traffic light scheduling or mapping, or also you can use it for controller parameter optimization. So it's quite a good optimizer. So I have here a simple example where it solved this Rosenbrook function. So there's several local and global minimas in the problem. So it's quite small. So I'm going to put some particles on the problem space. Change the example. Okay, so I have the function here, and then I'm going to put 100 particles. Sorry, I'm going to put 36 particles in the problem space, and then run through the optimizer. So this is I've custom made this PSO algorithm so that I can understand how it works. So I'm not going to go through the algorithm, but I'm just going to run the script. So here I've placed 36 particles across the problem space, and as you can see, it's the particles are communicating with each other so that they can move in the same direction towards a global minimum. So this is the final solution. So it's quite a good optimizer. It's an alternative to the genetic algorithm. Okay. So next, we can also combine algorithms. So you can make it into a hybrid model. So here I have an example on how we can use genetic algorithm and gradient descent optimizer to make it into a two-stage approach. So first is using a genetic algorithm to find a possible space, a possible area in the problem that may contain global minimum. Once it has found the area, it can fine-tune the parameters so that you can get more accurate parameters. So you can see here the first stage is using genetic algorithm to just estimate the area, and then it's using gradient descent optimizer to fine-tune the parameters to get more accurate results. So this is one example of hybrid methods. So you can mix and match between different optimizers. Okay, yeah, so my last topic I'm going to cover today is which language to use. So this there's a lot of questions about this. So it's totally depending on your problem. But for my perspective, Python is quite a popular language for data science and machine learning. But at Ricardo, we use it a lot for data mining or creating prototype models. And then for model in loop or parameterization or algorithm development, we are still using MATLAB because we have MATLAB has all the toolboxes and functions to help us to create algorithms quickly. And then for deployment, we can use both Python and MATLAB. You can put a MATLAB in a container, so that's also possible. So this is how we are doing things at Ricardo now. So both languages, they are still relevant and still important for the automotive sector. Even here, you can see there's a Tesla latest vacancy. They're still using MATLAB and Simulink for simulations. So MATLAB Simulink is still relevant and quite important for the automotive industry. Right, so before that, let me check something. I'm going to check something if I'm missing some of the example. Okay. Right, I think that's all from me. So at Ricardo, we are focused on improving efficiency and engineering processes through AI and ML. So we are trying to explore how we can apply those techniques in these areas: model parameterization, strategy emulation, fleet data analytics, and control optimization. So because adoption of ML in Powertrain is quite slow, so we are trying to explore creative ways on how we can use the intelligent techniques for Powertrain. So we are happy to discuss any opportunities or collaboration. Yeah, so any inquiries, you can contact me directly, or I have here my LinkedIn account if you need to ask me any questions or maybe need some advice on how to do modeling or optimization. Yep, so that's all from me today. So I'm going to hand back to the organizer.
Thank you, Dr. Farhan, for the amazing demonstration. Yeah, so we have learned today on how Dr. Farhan actually mapping the EC in Simulink and the MPT, how he convert a PDF into deep learning and AI into the trace system of Ricardo, but and then how he used GA in Formula One in developing a model to predict the useful life of the engine itself. So, but I realized that there is some students here actually from first year and second year. So just to explain in a very layman term, this is something that is a really good exposure regarding artificial intelligence using MATLAB for the current technology. Because what you learn in the syllabus during your first year, you learn how to use the MATLAB. And in this particular demonstration, you are actually being shown that AI system itself have a tools in the MATLAB itself. So in third year and the fourth year, you will learn control engineering. There will be numerical subjects. These are all subjects that you will learn how to convert physical technology or system into a model. And this particular model is what, just like Dr. Farhan has shown, which he used Simulink and other type of software, which he connect with MATLAB on the AI. So, of course, it might be too early, but this is something that you don't learn inside the syllabus. It is very good exposure. And in fact, this AI system using MATLAB, you can actually learn in open source. There is quite numerous people actually still studying it, still doing the coding. I myself are doing research in particle swarm optimization. And I myself learn from people out in the open source on the internet. So it's really amazing that if someone of you are enthusiast in coding, able to link in your projects, I would guarantee even lecturers going to hunt for you for collaborating researchers in the future. I would guarantee that because AI is something that is really uh, going to become famous in current studies in Malaysia. So basically, but I just want to ask to Dr. Farron, is there a reason why you choose GA and PSO? Because in AI itself, there's a lot of other types of algorithm. There's artificial neural network. I think that's the most famous one in automotive, I guess. And there's like beehives and ant colony. So how to choose what kind of algorithm suit for your model, for your work, for your industry?
Okay, so in the industry, we always start with the simplest optimizer, and then when the optimizer cannot solve the problem, we start to grow into or use more advanced methods. So you usually start with something small, even for modeling or something simple. Even for modeling, you start with a simple model that you can deploy, and then if the model cannot it's not suitable for that problem, then you start to grow the model, make it into more advanced, using advanced model. So always start with something simple. Don't go to the complex model. Even for deep neural network or even machine learning and deep neural network, sometimes people straight go to the deep neural network because they think it's cool, but actually it's not. You always start with simple models such as a regression model, then go for the advanced one. So for most of our application, we start with GA, so that's the simplest one, and we found it can solve a lot of problems. So for more complex, we use more advanced methods. Okay.
Thank you so much. Thank you again to Dr. Farron. So before moving to Q&A session, I invite everyone to follow our Facebook page and Instagram for more upcoming events in the link given in the chat box as well as the attendance. So our PIC will send the links inside the chat box for you to click, because SAE Malaysia will conduct more programs in the nearest future for everyone to join, especially for professional growth. In fact, in April, there will be another SAE Malaysia 8 lecture series, and we hope for your support by following SAE Malaysia and SAE UTM. SAE UTM also continuously engaging with secondary school students, promoting science, technology, engineering, and mathematics among youth and other design competitions since 2016. Your support by just following their Facebook and Instagram is very much appreciated. Now, let's move to Q&A session to the chat box.
Okay, there's a question about gradient clipping, so I'm not sure what's that. So I never heard of that term before, so I'm not sure. So any questions?
The option of my chat box suddenly disappeared, so I didn't open it. Wow, so what is the hardware spec for the recommend for AI and machine learning?
Oh, okay. Okay, for MATLAB, if you're training a deep neural network, then you need a GPU. So it must be an NVIDIA GPU. So I'm using NVIDIA GPU. I can't remember the model. It's RTX something. So yeah, you need GPUs to train a deep neural network. Otherwise, it will take days to finish. But for machine learning model, for regression model, I don't use any GPU. So you can train using normal CPU. It will take doesn't take that long compared to a deep neural network. Again, I'm not sure what is gradient clipping, so sorry. Oh yeah, one comment about hardwares. There are a lot of cloud services you can use now. They have a lot of visual machines, and they can be quite powerful. So you can just deploy your training process to the cloud services. That might help on speed up things. So Powertrain unit. How do I answer that? What's your advice for student interested to learn more? I'm not sure. I'm not sure how to answer that. Don't give up. It can be quite complicated. Just I cannot answer the last question, so it's up.
I think what Aiman Ramli is trying to advise students who actually interest in pursuing their study, focusing in powertrain. And about the master course is actually AI is a research that being quite heavy research in UTM. So you just need to find the right lecturers who do the research.
Okay, and then for how do you understand and master about AI and ML? So you need to go to a lot of conferences and read a lot of papers. But sometimes they can be quite complex and complicated, where they have a lot of formulas. But you need to understand the algorithms. Otherwise, you need to have a strong mathematical background to understand the algorithms so that you can master in those areas. So yeah, I know you have a lot of tools that you can just simply use from the internet, but most
Yes,
of the
yes,
time
the theory.
you need to understand how it works. So it's
Yes,
quite
yes.
important. Yeah.
But how about the powertrain students who interested? I mean, I think he asked in terms of how a student want to be specialized in powertrain.
I'm not sure how to answer that. I'm from the some sort of software background, so
I see.
yeah, it's difficult for me to answer. Sorry.
Hill, can I answer that question
Yeah,
here?
yes. I think Dr. Azman is the person suitable to answer
We're,
this question.
we are referring to Mr. Aiman Ramli, right? Question.
Yes, dear Mr. Aiman Ramli.
So I think because in not sure if Aiman is from UTM or not, but in UTM undergraduates for engineering students particularly in the School of Mechanical, either third year or the fourth year, you will have powertrain related subjects such as internal combustion engines, um, vehicle engineering and so forth. So those are supposed to provide you the basic, the fundamentals of powertrain subjects and so forth. That should include the powertrain unit as well. But then if you want to study further, then you should be able to consider whether you want to continue your masters by research in the powertrain. And we have since in UTM we have links with industry, including Dr. Farin as well, so we can have industry people to be your second supervisor for any research related to powertrain. So, so that should, I hope that answers Mr. Aiman's question. Yeah.
Okay, that question I can answer about MATLAB and Python. So Actually, MATLAB is much easier to use because they have all the functions toolboxes that is guaranteed to function properly, and you don't have to install any packages or don't have any dependency issues. But of course, it's related to cost. It's expensive for maybe for students or institutions. They're quite cheap, but for business for commercial, it's quite expensive. The toolboxes is let's say if you're using a reinforcement learning toolbox, then that might cost you about £600, maybe about 3,000 ringgit per year. So it's quite expensive. So to be honest, MATLAB is quite easy to use compared to Python. Maybe because I've been using it for maybe 10 years now. But I think MATLAB does have tendency to crash depending on how you use it. And but now currently I'm also using Python for most of our tools, but I prefer Python for deployment deployment purposes, because if you want to show something on the dashboard or deploy the codes or algorithms into cloud services or clusters, I do need Python, so it's much easier for me to code on and to show results. So it's totally depending on the problem and depending on the project itself. Okay, so then the next question is about multi-objective generator. Oh yes, I do have I use generated algorithm for control optimization for our Japanese client. So we have been doing mix and match between different optimizers, including genetic algorithm for getting controller gain maps, like the one that I've showed in the presentation. So it's quite similar process, but for actual diesel plant model. And also for reinforcement learning, yes, I have experience in doing that. Previously, I've involved in a project where we use reinforcement learning to predict energy prices for rail sector. So so I use it to determine when to release or receive energy, so that to keep energy prices minimum. So that's using reinforcement learning to learn to learn the pattern, the price pattern for the energy prices. So yeah, I do have reinforcement learning experiences.
Dr. Farid.
Yep.
So while waiting for the questions, let me just ask you one question. An advice to students who is in the first year and second year at the moment, since they are very early in the university. What is your advice on how they should start to look into, if they are interested in machine learning? What they should do now?
Okay, my best advice is go to the internet and download examples. There are a lot of examples. There's too much example. So you can try out the examples from Python. They are free. So I think you better start now, better than later. Try to understand how the example works, and it might be useful for you, because even though we are from the industry, if we are going to deliver something or deliver projects results to our customer, yeah, sometimes we also use examples and then try to work out how to construct the algorithms from examples as well. So examples are quite important. I think you need to start early playing with MATLAB and Python. So yeah. and also try to improve in your mathematical skill. So that's quite important too, especially numerical methods. So I didn't learn numerical methods when I was at university, so it was difficult for me to learn. I had to learn it myself during my first year of PhD, and I was struggling. So my advice to you is to learn numerical methods from today. It's quite important for the future, especially when we are moving towards digitalization and using a lot of ML and AI. So you need to have good mathematical skills. For Python IDE, I'm using PyCharm at the moment, but later I'm going to use VS Code. So, but I think PyCharm is quite easy to use because the package installation is quite easy compared to the VS Code. Yeah, again, math concept. So yeah, those things being taught in numerical methods is important for ML and AI. Yeah, just go through the syllabus and you should be fine. Anything else?
I think one of the challenge that in terms of for mechanical students understanding MATLAB and this numerical method, one of the challenges also is how to relate both of them, how to connect these parameters. So that's why it's very important to learn the maths concept, and then you that way then you learn how to actually connect with the AI, including the MATLAB itself.
Yes. Yeah, you're right.
It's okay. There's we have actually plenty of time, 10 minutes. If anyone want to ask more questions to Dr. Farron. Yeah, may I ask a question to Dr. Farron and Dr. Azman?
Okay.
So right now, I know in terms of research, AI is quite rapidly being used. But how about in your working experience, the industry itself? How to, in terms of, is it really being promoted? Is it, does the engineers are learning and trying to implement? Is it right now the students must equip themselves as much as they can before working?
Okay, but I think most of the companies now are gearing up towards digitalization, and they're using a lot of machine learning. Even they are employing a lot of engineers who knows machine learning and AI that can make their process efficient. So I've seen this in a lot of companies, and yeah, it's quite important subject today. Okay. I lost my words. I don't remember what to say. It's quite a long question. I found that. Okay. Yes, reverse engineering code is one way to learn. So there's a lot of codes in on the internet. For MATLAB, there's a lot of codes in file exchange. So you can use those. Try to reverse engineer the codes so that you can have better understanding on how it works. So that's quite a good way to speed up your learning process. Of course, don't copy the codes, but try to understand how it works, and then try to make your the version of the code. And
How does AI actually get intelligent tasks or human-like tasks to perform?
so, okay, you don't need to code them much today because we have a lot of tools and functions to train an AI. But the training process, it can take quite a while, depending on the problem. It can take days or weeks. So yeah, what else? How long does it take to code them? Yeah, it doesn't take long to code them. It's just understanding the problem and how to use those functions to that particular problems. Especially for reinforcement learning, you can easily get the codes. You don't have to write anything else. You just link the environment or the agents to the functions. So to understand the problem is it will take much longer time compared to the coding of the algorithm itself. Of course, AI cannot reach human-like tasks at the moment because they are not that smart. It's totally depending on how you train them. If you train them with rubbish, they will give us rubbish, right? So, but we are heading towards more third generation of AI, where they call it general artificial intelligence. So they have neural networks such as spiking neural network. So that type of neural network is much more human-like in terms of how it is going to make decisions. So yeah, we're heading to the third generation of AI now. So just be prepared. Learn about it now. It might be important. Data. What? I don't understand the question. Does it related to the previous question? Or? Yeah, of course you can use the data that you have harvested or stored in a database. Yeah, like at Ricardo, we do have a lot of vehicle data from our previous trips that we have collected, and yeah, those data are quite useful to us for creating algorithms or creating new tools. So yeah, any data that you have might be important. So don't delete them. Can you share any? Yeah, for reinforcement learning, I cannot share anything because we do have projects using reinforcement learning. So maybe when we have made the content public, we can share it with. I can share it with UTM. So at the moment, sorry, I cannot share any example yet on reinforcement learning.
But I think if our audience is not really interested in terms of that, he can actually personally reach you on how to practice together with the engineering problems.
Yes, in for MATLAB, in MATLAB, there's a reinforcement learning toolbox. So there's a lot of examples in the toolbox, so you can learn from there. They are quite good examples, such as there are some examples of they are replacing controllers with reinforcement learning agent. So that's quite new and quite good for you to learn. So I know MATLAB toolbox is quite cheap for the educational sector. So you can start learning using the examples. It's quite good.
We are going to stop Q&A session in 2 minutes because it's already 9:43.
For MATLAB, I'm using 2020B now. I recommend using 2018B and above. But if you can get a copy of the MATLAB 2020B, maybe it's much better for you because they have good reinforcement learning examples. So always try to get newer MATLAB version because they keep updating the toolboxes, especially for those for machine learning toolboxes.
There's only 1 minute left for anyone to ask questions. I think it's already reached 9:45. I think we can end here, Dr. Faris.
Okay.
Hill, may I just conclude with one question to Dr. Farin?
Oh, of course.
Dr. Farin, last question. Okay, can you give some advice to students who's doing undergraduates today on achieving their dreams to become engineers?
Never give up. Yeah, I know sometimes people complaining about salary because salary factor is quite demotivating factor in engineering. But don't give up. Try your best. Learn as much as you can. So you might be valuable in Malaysia or outside Malaysia. So depend on the opportunities. So don't give up. I know that's I know what's this current situation, but try your best, learn as much as you can. We are heading towards digitalization, and whatever you learn now in machine learning and AI might be important. Yeah, continue doing engineering. So yeah, we need smart engineers like you guys.
Yes, because I think most of the people are going to be influencers than engineers nowadays.
Yeah.
Okay, Hill, thank you very much, Hill.
So, well, ladies and gentlemen, that wraps up our event for tonight. On behalf of SAE Malaysia and SAE UTM, I would like to thank you to our special guests, Dr. Farhan and Dr. Azman, as well as all audiences for joining us here tonight. I hope everyone have an idea on promoting or implement AI system in the local industry. Hope to see you guys again in upcoming program. Don't forget to fill in the Google form before leaving this event, and please do follow us and give us a like in our Facebook page SAE Malaysia and SAE UTM, including SAE UTM's Instagram with just a single click. Assalamualaikum and a very good night.
Thank you.